Okay, so welcome everyone to this One World IAMP Mathematical Physics Seminar. For those of you who are not regulars in the series, this is the seminar of IAMP, International Association of Mathematical Physics. And if you want to find out more about our organization and the seminar series and the mailing list, there will be a link available on the chat. This talk, as all our talks, is going to be recorded and you can rewatch it on our YouTube channel. Now, let me introduce today's speaker. It's a great pleasure to have Slava Rychkov here talking about tensor renormalization group at low temperature. Slava, please take it from here. Thank you.
Thanks, Kasia, for the introduction. I'm very interested in speaking for this audience. I see many people in the audience who did important work using RG, so I'm curious what they will think about this approach. So Tom and I gave already some talks about this work, about our previous paper, and tried to make this talk a little bit different from the talks that you might have heard already. But let me start nevertheless with some broad introduction. So in physics, we really, when we talk about phases of lattice models, really renormalization group theory, it takes the front seat. So with each phase of lattice model, we typically associate a fixed point, which is like a basin of attraction for this phase. So you may have like a phase one with its fixed point and another phase. Sometimes the fixed points seated at phase boundaries. So this is all the rage of theoretical physics study of phase transitions. A typical case is when you have an ordered and a disordered phase. So in that case, we speak of a low temperature fixed point for the ordered phase. We speak of a high temperature fixed point for the disordered phase. And often, for example, for the Ising model, there should be a critical fixed point in the middle of this diagram, which should describe the critical phase of the Ising model. And for the low temperature fixed point neighborhood and with the high temperature fixed point neighborhood, there is available rigorous treatment, mathematically rigorous treatment. But the critical fixed point so far remains challenging. And so why is that? Well, first of all, it is believed that this critical fixed point should live in some infinite dimensional space of couplings, unlike the low temperature and the high temperature fixed points. Second, there is typically no small parameter unless you cook up a model which has such a small parameter. And so if we are to find such a critical fixed point, we probably need a computer-assisted approach. So for hierarchical models, this has been done long ago, but for lattice models that we are interested in, like 3D Ising and other lattice models, this is wide open. And in fact, this is not just a conceptual problem, this is also a practically important problem, because if we construct this fixed point rigorously, as a byproduct, we will get critical exponents of these lattice models with rigorous error bars. And this, of course, would be very interesting for mathematics and also for physics. And so basically, we need to attack this problem, we need a non-perturbative RG approach, which would satisfy two conditions. So first of all, it should be rigorous. And second, and this is maybe unusual for this audience, it should be a calculable approach. So I would like to insist on this point. By calculable, I mean is that it should be possible to take the RG map. So we would like to construct some rigorous RG map, but we would also like to be able to truncate this RG map to a large but finite set of couplings and to evaluate what happens numerically. And this is because we know that at the end of the day, we will have to use a computer-assisted approach. And so today, I would like to talk about this Tensor RG, which, to my knowledge, is basically the only currently on the market approach which satisfies these two conditions, which is can be both made rigorous and calculable. So if you know of any other approach which satisfies these conditions, it would be very interesting. I would be very happy to know about it. And so let me give you a brief introduction to Tensor RG without much technical details. So if you want to use Tensor RG, then the first step is that you take your lattice model and you should rewrite its partition function as a contraction of tensors, so as a tensor network. So here I drew a tensor network. So you have this basic object in this tensor network is this tensor A. So it's a 4 tensor. And okay, for starters, let's suppose that every index of this tensor runs from 1 to some finite value chi, which is called the bond dimension. And then you take these tensors and you contract them as shown. So every time there is a bond connecting the two tensors, it means that that index has to be contracted. So I'm on a finite lattice. So there is L tensors in the horizontal direction, L tensors in vertical direction. And I am also taking periodic boundary conditions, which means that the upper index of this tensor has to be contracted with the lower index of that tensor and so on. So this is what we mean by a tensor network. So that's just a preparatory step. And then you have to devise a coarse graining step, which you then are going to iterate. And so this coarse graining step is going to take this tensor network made of tensor A, and it's going to create another tensor network, which is going to be made of tensor A prime. So it's going to be A prime, just not too many of those, and so on. So this, you contract things periodically, and you would like to arrange it in such a way that this new tensor network has a smaller number of tensors. So the number of tensors is reduced by a certain factor b. That's the first condition. And the second condition is that you would like the partition function to be preserved. So z prime, which depends on A prime, has to be equal to z. So if this condition is satisfied, then you say that you have a tensor network RG transformation. So by the way, I don't monitor the chat. So if there are any questions in the chat, then I would like the organizers to alert me.
Yeah, I will tell you. Nothing at the moment.
Otherwise, please just interrupt me.
Yeah.
So there are some remarks about this tensor RG. Okay, the first thing is that if you want to do this exactly, and we would like eventually to do this transformation exactly, then you will inevitably find that this tensor A prime, that its bond dimension chi prime is going to become larger. So it's going to grow. And so when people apply this tensor RG numerically, and there's a lot of literature trying to do this numerically, very sophisticated algorithms, you have to truncate. So all these algorithms, they need to truncate the bond dimension somewhere to keep it from growing, to make the tensor fit into a computer. And so what these all algorithms differ is in how they implement this coarse graining. There's a lot of flexibility, and how you perform this truncation. Again, there's a lot of optimization tricks that you can implement to minimize the error, the truncation error. And if you do it properly, then, for example, you can find that if you apply these tricks to the two-dimensional Ising model, which of course is exactly solvable, but it's a good benchmarking model, you find a fixed point, a critical fixed point, you find the critical exponents by linearizing near this fixed point, and you find that they agree very well with exact values. So the method really works. It is calculable and it is very accurate. And so the problem that eventually Tom and I would like to solve is to apply this method to find an exact critical fixed point for 2D Ising, and perhaps for 3D Ising, and perhaps for other models. But that's a problem for the future. So far, we were able to do a few things. So we developed some rigorous Tensor RG theory, which doesn't involve truncation. So that was not very sophisticated, but new, because all numerical literature before us, they did use truncation at some point. So in particular, we do it for infinite dimensional tensors. So that's kind of inevitable. If you want to do things rigorously, then you should start with infinite dimensional tensors, and you should control them in some norm. I'm going to specify this later on. And then we did two kind of exercises, which if you can do this, then this is a non-starter. So we start with simple problems. So that was our first paper. We showed that the high temperature fixed point is stable. So I'll explain this result a little bit. And this result has a simple corollary that the free energy is analytic at high temperature. So it gives you an RG proof of free energy analyticity, which doesn't rely on cluster expansion or anything like that. And the second thing, and that's going to be the focus of my today's talk, is that we use this method also at low temperatures and in zero and in non-zero magnetic field. And so we could show using this method that there is a first order phase transition at low temperature. And of course, the result by itself is not new. There are other methods which get you there. There's Pirogov-Sinai, and there are methods based on contour coarse graining. But for us, when we did this, the amazing thing was how little modification actually is required in this Tensor RG approach to do things at low temperature versus high temperature. It's basically the same thing. So the RG map is basically the same RG map as for high temperature. And that's quite surprising because, usually if you want to do things at low temperature at small magnetic fields, much of the rigorous literature says that you have to do things differently. You should switch to some other representation, to contour representation or whatnot. And here, somehow, this Tensor RG turns out to be flexible enough that it captures both low temperature and high temperature. So that basically finishes my introductory part, which is prepared slides, and from now on I'll basically switch to handwriting. But if you have any questions about this introductory part, then please ask them now. Okay. So I'll do the nearest neighbor Ising model on 2D square lattice in non-zero magnetic field. That's the example that we consider in both of our papers with Tom. And as I said, the first thing that you have to do is that you have to take your model and transform it to a tensor network. So that's a simple transformation. And I'll...
Slava, there is a question from the chat. Do you need nearest neighbor interactions or also long range?
So it's not difficult to show. So I'm going to do here nearest neighbor case. So you transform the model to the tensor network form. But it's not difficult to show that any model with a finite range interaction can be transformed to a tensor network form. So you don't need nearest neighbor.
Thank you.
So how do you do this? You take the model and you take the spin lattice and you turn it at 45 degrees, and then you divide the squares of the lattice in a checkerboard pattern. So you take gray squares and white squares. So that's let me do it. Let me do this coloring. And then with every gray square, so let me call it here, let me call spins S1, S2, S3, S4, at the vertices of the square, I'm going to associate this combination, which I will call HG, G for gray, which is going to be, it's going to be beta. So I'm going to include into it all pairwise interactions between the four spins. But I'm going to include into this HG only half of the magnetic field interactions. And that's because every spin belongs to two gray squares. So if I do this, if I introduce this gray square HG, then H now is a sum of HGs over all gray squares. And so this allows me to define the tensor A. So I'm going to define my tensor A, which is going to be indexed by S1, S2, S3, and S4. So it's index Si just belongs to the index space is 0 is plus or minus 1. So the bond dimension is equal to 2. And the tensor element of this tensor A is equal to e to the hg. I take this hg and I exponentiate it. And this definition, if you think about this for a second, it guarantees that the partition function of the model is equal to the contraction of A's. So this is a very trivial transformation. And a remark for the later part of the talk is that this transformation gives you a tensor A, which, since it's an exponential, all its tensor components are non-negative. So that's going to connect to some remark later on. Okay, so if there are no questions, I take this tensor A, and now I would like to first say a few things about the high temperature region, and then I'm going to move to the low temperature region. So the high temperature region means that I have to take, the high temperature fixed point would correspond to beta equals 0 and h equals 0. So you look at this tensor A, how it is defined, and you realize that in this limit, all tensor components of A for arbitrary Si are equal to 1. So this is for any Si. So then what you are supposed to do in this situation is that you're going to do a rotation. So this is something that we are going to call a gauge transformation below. So I'm going to introduce two states, 0 and 1, which are just combinations of plus and minus 1, orthogonal combinations. And I'm going to rotate my tensor. I'm going to apply orthogonal transformation on every leg of the tensor. So that, of course, it preserves the contraction of the tensor network. And so if I do this transformation, then in the new choice of basis, the only non-zero component of my tensor is A0, 0, 0, and it is equal to 1. Well, 1/16 to be precise, but let me rescale, so it's equal to 1. And so this is a very simple tensor. It has only one non-zero component, and I'm going to call it A star, and this is my high temperature fixed point. So why do I call it high temperature fixed point? Because if I take A star and I contract it with itself 4 times, so that's kind of a very simple kind of coarse graining transformation, just contract the tensor with itself. You know, since the tensor A star, it only has 0, 0 components, so all indices here are 0. So I can just rename this pair of indices 0, 0. I can rename it as 0. And so it means that this contraction is, again, A star. So it is a fixed point. Okay, fair enough. But now I would like to consider not just the fixed point, I would like to consider its neighborhood. So neighborhood means that I have now to take small beta and small h. So if I take this neighborhood, then A star, so that I'm going to get a tensor. So that I still know what my tensor is. So it's just given by this transformation that I showed to you. So I can see what happens when I do this perturbation, and you find that the tensor in this region is equal to, once you apply this rotation, you get a tensor which is of the form A star plus B. So I call the deviation from A star by B. And this B is a tensor which is order B plus H. It's small in this limit. And you know, this B, this initial tensor that you get, it still has chi equal 2, of course. For the theorem that I'm about to start, I will have to deal with tensors of arbitrary large bond dimension, actually of infinite bond dimension. And so I'm going to index these tensors of infinite bond dimension by IJKL, and every index is going to be a non-negative integer. So the index 0 plays a special role, because that's the index of the high temperature fixed point tensor, and then there's an infinite number of other indices. And so for these tensors, I have to come up with some norm to measure their size. And actually it turns out that the simplest norm is the most natural norm. So the norm that we use in our work is just the Hilbert-Schmidt norm. So why this norm? Because that's the norm which behaves well under the contraction procedure. So we have tensors, we have to contract them. We would like to bound the norm of the contraction by the norm of tensor of the initial tensor. So that's the norm that you have to use. So in particular, if this tensor B has a finite norm, this is sufficient to guarantee that the partition function on a finite lattice is finite. So you can consider a partition function on a finite lattice made of this tensor. And so this procedure guarantees that it's a finite quantity. So yeah, so that's kind of nice. You see, usually in renormalization group studies, people often have to cook up some complicated norms to make things work. So here, no complicated norm is needed. It's just the simplest norm is the one that they're going to use. And with this norm, I would like to formulate this theorem. So that's the theorem that we proved in our first paper. So it's the theorem which says that the high temperature fixed point is stable. So it says that for any gamma less than 1, there exists an epsilon and a Tensor RG map which is defined for this perturbation B having norm smaller than epsilon. And this RG map has the following properties. So it maps the tensor A to another tensor A prime, which is of this following form. So there is a star plus B prime, a new perturbation B prime. And there is, as usual, when you apply renormalization group transformation, there is some free energy which is generated by the RG step. So here this free energy appears in the form of a rescaling factor, which I'm going to write as e to the g, which is just a scalar multiplying this tensor A star plus B prime. So A is mapped to A prime, and the size of the lattice is reduced by 4. That's how it works. And moreover, so G and B prime are analytic in B, and they satisfy certain bounds. So G is order of B squared, and finally, the norm of B prime is contracted. It's less than gamma norm of B. So as I said, since it's contracted, it means that the high temperature fixed point, once you iterate this RG map, you are going to get converged to it, so it is stable. So I'm going to make some comments about in a second about how this theorem is proved, some very non-technical comments. But before I go to these comments, I would like to give you a very simple corollary of this theorem. So the corollary is that the free energy is analytic near the high temperature fixed point. So I define the free energy, as a function of B and L in finite volume. It's a free energy per side, so it's 1 over L squared times log of the partition function. And this is a definition. And the properties are that, first of all, I can show that if I take a lattice of size 4 to the n, then for any n, this free energy is bounded and analytic, for B is small. And I can also show that it has an infinite volume limit, which is also analytic. And of course, we know this by cluster expansion and whatnot. But the amazing thing is that with the RG method, you just have a 2-line proof of this fact. And this proof is just a proof which comes straight out of a physics textbook, except that it's rigorous. So I'm not going to give many proofs in this talk, but that's the one I would like to give. So how is this proven? My RG map by construction, it preserves the partition function. So the partition function is preserved, but the number of sites is reduced. So let me compare the free energy on the lattice before and after the RG step. So before the RG step, okay, that's my quantity that I would like to study. But after the RG step, so I have the new free energy on a smaller lattice. But since the number of sites is reduced, I have to divide by this coefficient 1/16. Plus, because I had this e to the g rescaling factor, I have to add here also 1/16 g of b. Notice that g doesn't depend on L, it only depends on b. And so that is one step of the RG. But now let me consider the full RG trajectory. So I'm going to consider the RG trajectory. So b0 equals b and bj plus 1 equals b prime of bj. And I'm going to iterate this equation. So once I iterate it, I'm going to iterate it until the lattice becomes 4 by 4. And then I'm going to stop. So I'm going to get then the last term, which is 1/16 to the n, f of b n minus 1, 4, plus I'm going to get the sum from 1 to n of all of these terms, of g terms. So it's g of bj minus 1, 16 to the minus j. And so now it's basically obvious, because again, this term is on a 4 by 4 lattice, so you don't have to have any sophisticated techniques to bound it. It's just you can expand everything, and you know that this free energy is finite and bounded and analytic, everything. And it has this coefficient 1/16 to the n, so it goes to 0 in the n going to infinity limit. The function g is also bounded, so this series converges, and so you get this very simple formula for the free energy, which is just the sum, extending the sum to infinity. And so that's it. You proved it. So I don't know about you, but I really like this argument. So that's so now I showed you the corollary, but I would like to say some words about how this theorem is proven. I'm not going to give the full proof, but I'm just going to show you the main building blocks of Tensor RG. So you have to combine these blocks. You have to have a little bit of imagination how you combine them, but to appreciate this imagination, you have to play with it. But I'll just show you how simple these blocks are. In fact, the first block is this gauge transformation. We have already seen it. When we transformed the high temperature fixed point tensor from one basis to another basis by an orthogonal transformation, that was a gauge transformation. So that was an orthogonal gauge transformation, but you can consider also more general gauge transformations when you multiply a tensor on one leg by g and on the opposite leg by the inverse g. If g is a bounded map and its inverse is also bounded, then the new tensor is again Hilbert-Schmidt. If once you contract these new tensors A primes, you get, on the horizontal legs, all these g's and g primes, they will just cancel. There's some comment that there seems to be a misprint. What kind of misprint? bj minus 1. There might be some minor misprints. I don't see it. I think it should be bj minus 1, but if there is a misprint, it's a very unimportant one. So I wouldn't dwell on it too much, but I think there's no misprint.
Actually, it's 16 to the power n minus 1, but it's very minor.
Yeah. Here I agree. Thank you. So this is the gauge transformation. You can apply it on the horizontal legs. You can apply it on vertical legs. One thing that I would like to add here is that we started with a tensor which was non-negative or positive because it was exponential of this h on gray squares. But once you start applying these gauge transformations, this condition is no longer satisfied. So you may get some negative entries. Of course, if you do things properly, they're going to be small. And this, in fact, this allowing for this negativity, I think that's probably the key property of this Tensor RG, which gives us enough flexibility to achieve all these things that we claim we can achieve with it. So I don't want to speak more about it, but for me, I think this is an important point. The second building block is this simple RG. We have seen it again. When we took the high temperature fixed point tensor and we contracted it with itself, and we got the same high temperature fixed point tensor. Of course, you can apply the same idea to any tensor, not just the high temperature fixed points. This is an NRG transformation. So here I kind of drew these legs coming together. What I would like to emphasize here is that I would like to view this new index, kind of double index, I would like to view it as a new index. So my original tensor was indexed by non-negative integers n0. So this RG transform tensor is going to be indexed initially by n0 cross n0. There are two indices. But of course, I can renumber this. So n0 cross n0 is equivalent to n0 up to renumbering. So it's up to me to choose this renumbering how I want. But that's, once I renumber the tensor, I get the tensor of the same type as the one I started with. So it's an RG transformation. And the final ingredient is a little bit more subtle. So it's called disentanglers. So let me talk about this a little bit. The idea of disentangling is the following. So you start with a contraction of two tensors, x and y. And you imagine that, in your network, this x and y is like a building element of your network, of your tensor network. So you put this x and y next to each other, on top of each other, and that's your full network. It's made of x and y's. Now, you do two things. First, you act on x and y contraction, left and right, by these disentanglers, R and R minus. So R minus is just the inverse of R. So you see, this disentangler is just like a gauge transformation, but it acts on two indices. It acts on two horizontal legs. So it has to be bounded as a L2 on these two horizontal legs, but otherwise it's just like a gauge transformation. Again, up to you to choose what this disentangler is. And then once you choose it, you have to do a second thing. You have to decompose this new tensor contracted with R and R inverse as a contraction of two new tensors, X prime and Y prime, I call them. And the goal of the whole procedure is that this leg, so X prime and Y prime, they're contracted along this leg, which I denoted by a wiggly line. So it's called disentangler because you would like to achieve that this wiggly leg has reduced entanglement. Now, entanglement is a quantity from quantum mechanics. What it means here, we're just borrowing the term as everyone else. What it means here in practice is that you would like that on this VG line, as few indices as possible contribute to this contraction. So you can try to quantify it more precisely, we won't need it, but imagine that there is the index 0, which contributes most, and then there are all the other indices which also contribute a bit to this contraction. Well, you would like to reduce their contribution as much as possible. That would be an example of reducing the entanglement. And why is this useful? Because then you can do this reconnection procedure. So you imagine that you have this column of x and y tensors, yx, 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 and then you produce the disentanglement tensors x prime, y prime, x prime, y prime, x prime, and so on. And then you do the reconnection. So you contract x prime and y prime, but in opposite order. So you cut this Vigli line bond, and you call a new tensor, which is the contraction of y prime on top and x prime at the bottom. And you can kind of imagine why this is an interesting thing to do, because once we disentangle, so this Vigli line, it's very economical. So it, for example, it may be dominated by the 0 index. So once you do this contraction and you form this new tensor in the round ellipse, you can imagine that that tensor, most of its weight is going to be concentrated on the 0 index, and all the other indices are going to be suppressed. But that's what we want to achieve. We want our transformation to be a contraction. So we would like all contributions except for the 0, 0, 0, 0 component to go down. And that's what you achieve by this disentangling. So if you see it for the first time, it's probably very weird, but I hope you get the feel. So I have kind of a page on why these disentanglers are useful and what kind of problem they fight. But I would like to come back to this point if there is interest at the end of my talk, in the interest of time. And so what next? That basically it. So you combine these ingredients, and then you prove theorem 1, and then you prove that the free energy is analytic. So that's the end of it near high temperature. So let me now move to the low temperature, unless there are questions. So at the low temperature, so recall that we have this tensor A, which is defined as e to the hg. So the low temperature means that we are taking beta large. And if you take beta large, then this tensor A is going to have two components which are order 1, which are going to be e to the 2h plus component e to the 2h, and minus component is going to be e to the minus 2h. And these are going to be the largest components. So all the other components are going to be suppressed by e to the minus 4 beta. So that's easy to see. And so let us rescale by the sum of these two things, by the sum of these two coefficients. And once I rescale, I can write my tensor A as the following linear combination. Let me denote it as alpha A of alpha B. So it's alpha A plus 1 minus alpha B A minus plus B. And alpha here is e to the 2h divided by the sum. So it's a parameter between 0 and 1. B, as I said, it's a small tensor, low temperatures. And this A plus and A minus, which I introduced here. These are the tensors which have the only component. They have a single component, q, 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 q. And all the other components are zero. So q is equal plus or minus. So I wrote my tensor, my initial tensor as this linear combination. So now what happens as a function of alpha and b? So I'm going to draw alpha here on the horizontal line, b schematically on the vertical line, the size of b. So b is small. So I can, take in the temperature small enough. Well, I can take b smaller than epsilon. But what happens in this alpha direction? So if I take alpha sufficiently close to 1 or 0, so this is alpha equal 1/2 point. If I take, a neighborhood of alpha equal 1, let's say if alpha is larger than 1 minus delta, and the same neighborhood close to 0, so alpha less than delta, for certain delta. Then in this region, and in this region, my tensor is this linear combination. It's either close to A plus, very close to A plus, or very close to A minus. And A plus and A minus are just have the same form as the high temperature fixed point. So in these regions, theorem 1 applies. So I know that the free energy there is analytical. But if I stay in this region in between, then theorem 1 definitely doesn't apply. So I have to have some new construction. And moreover, we know that here there's going to be a first order phase transition. So definitely the free energy is not going to be analytic. So we have to do a new RG study. So what do you do? Well, you first consider for motivation, for intuition, you consider the case b equal to 0. And you see what happens. So if b is equal to 0, then okay, your tensor is really simple. So it's just alpha a plus 1 minus alpha a minus. It's very easy to contract this tensor with itself. You compute the partition function. The partition function is just alpha to the n plus 1 minus alpha to the n, where n is the number of tensors in your network. So in particular, the free energy is just the log of the mean of alpha and 1 minus alpha. So you have, as a function of alpha, you have this free energy and it has singularity. The derivative of the free energy has a singularity and alpha 1/2. That's what we expect. We have the first order phase transition there. And so what we would like to do, we would like to take this result and generalize it to the non-zero B. And using the RG, we are going to be able to do this very easily. So the first step is that, okay, this was by an explicit computation, so we would like to rederive the same result by an RG transformation. So how do we do this? So again, we are still at b equals 0, but we use now RG for the same problem. So our RG is going to be the simple RG. So I'm going to take A and map it to a contraction of A's. But now, okay, preparing to what's going to happen next, I'm going to take 4 by 4. The simple RG was 2 by 2, but here I'm going to take a contraction of 4 by 4 network of A's. Yeah, well, you get what I'm doing. And so what's going to happen? Well, it's very easy to understand what's going to happen. So alpha is going to change to alpha prime, which is, let me call this function R of alpha, which is alpha to the 16th. So there's, and now, I'm going to normalize this dividing by alpha to the 16 plus 1 minus alpha to the 16. And my tensor A is going to be mapped into exponential of a function which I'm going to call G0 of alpha times alpha prime A plus 1 minus alpha prime A minus. And this function G0 of alpha is equal to the log of this rescaling factor, alpha to the 16 plus 1 minus alpha to the 16. Very easy. And so now I'm going to give an RG formula for the free energy. So I'm going to consider an RG trajectory. So alpha 0 is equal to 0 to alpha, and then alpha j is equal to r of alpha j minus 1. And the following formula is true. So f of alpha is equal to the sum from j equal 1 to infinity, 16 to the minus j, g0 of alpha j minus 1. You're not surprised. You've seen exactly the same formula at the high temperature. Here I'm using it at low temperature. And this formula explains why the free energy is has a discontinuous first derivative at alpha equals 1/2. Because the crucial thing is that r prime at 1/2 is equal 16 that you can check. And this 16 is exactly the same 16 as appears in this rescaling. So that is a well-known fact in physics literature that these two things combined together, they give you a discontinuity in the magnetization. So magnetization is the derivative of the free energy. And so what happens basically is this: if you consider the sum of these terms here, the first term is something like that. So each individual term is of course analytic. The first term is something like that. The second term is reduced in size because of the 16 minus j, but it's kind of sharper near alpha equal to 0. Then the next term is reduced even more, but it is even sharper. So if you take the sum of all these terms, it's easy to show that you get a function which has a discontinuous first derivative. It's precisely what happens. And so, okay, now we are in business because we have an RG explanation of discontinuous first derivative. It works at 0b. We are going to prove a theorem which says that exactly the same RG transformation with exactly the same properties works for non-zero b. And that theorem is going to imply that also at non-zero b there is a first order phase transition. So that's a very robust strategy, and that's what we implemented with Tom in our upcoming paper. So I'm going to formulate a theorem, but perhaps there are any questions. Okay, so here's theorem 2. So it says that, again, for any gamma less than 1, there exists an epsilon and an RG map, which is defined for alpha belonging to this interval delta 1 minus delta and b less than epsilon. And it maps A of alpha b to A prime, which is e to the g alpha A plus alpha. No, let me just write it briefly as A of alpha prime b prime, and L goes to L over 4. And G, this free energy that you accumulate at every RG step, is equal to G0 of alpha plus order b squared, alpha prime is equal to r of alpha plus order b squared, and b prime is contracted. And the amazing thing is that the proof of this theorem is exactly the same as the proof of theorem 1. Okay, you have to, like, instead of having one index, you have to have two indices, two special indices, but everything else is like exactly the same. And that's really amazing, because normally you say at low energies, you have to, at low temperature, you have to work much harder, you have to invent some special things. Here, you don't have to invent anything. It's just exactly the same thing. Pretty amazing. And, you know, you wouldn't be surprised that having this theorem, so, okay, there's a bunch of corollaries, and I don't have time to state all of them, but basically, you know, once you have this RG map, you know that there is a stable manifold, so there's a stable manifold theorem, and it tells you that there's a stable manifold, alpha equals alpha critical of B, and you know that if you, so this is the B direction and this is the alpha direction, and you know that if you start above the stable manifold and iterate RG map, then you're going to converge towards alpha equal 1, and until you get into the neighborhood where we know that the free energy is analytic. And if you start below the stable manifold, you converge below. You have a formula for the free energy, which is just a combination of terms from every RG step plus the final term, which you accumulate when you get to the region where the free energy is analytic. So this formula proves that the free energy is analytic except on the stable manifold. Then it's easy to show that it's continuous also on the stable manifold. And finally, it's possible to show that now if you consider the magnetization of alpha and B, which is the derivative of the free energy, then you can show that this is equal to the magnetization. Let's say what you can show is that if you take this magnetization and you take the one-sided limit from one side or from the other side, approaching the stable manifold, then this is the same as the magnetization at the zero temperature, the same one-sided limit, plus a correction which is order B. And okay, so this is a little bit, it's a little bit interesting how this correction arises. And again, the amazing thing is that the proof of this theorem, you take any non-rigorous physics textbook, which explains to you what happens for the free energy, what happens for the magnetization near the phase transition point, and you just kind of follow this non-rigorous proof, except that with this bounds, with this norm, it's just absolutely no work to transform it into a rigorous proof. So basically what happens is that as you take this limit approaching the stable manifold, so your trajectory spends more and more time near this unstable fixed point. So if you call the point alpha star the point of the closest approach, so you have two regions in the RG trajectory, region 1 and region 2. And region 1 is the same if you approach below and above the stable manifold. So that gives you a deviation. So this gives you a deviation from the magnetization at zero temperature. And region 2 is of course different on both sides, but it's the same region it's the same trajectory basically that the zero temperature model follows. So you get the same magnetization up to a correction. So it's extremely robust, extremely natural. You just follow your nose, you get what you want. Okay, my time is up, so I'll just fast forward to my conclusions, which are very short. So far, we basically have shown that this Tensor RG provides a rigorous and unified framework. So it works at high and low temperature with minimal changes. Of course, this is all just an appetizer. So our main goal remains to extend this whole technology to the critical point in a computer-assisted approach. So that's something that we are working on, and we hope to report about this in not too much time. Thank you.
Thank you. Thank you very much for this very interesting talk. Okay, so the floor is open for questions. You can just unmute yourself and ask the question.
Yeah, can I ask a question?
Of course.
Yeah, thank you very much, Slava. This was beautiful. I'm impressed. There are many questions, but I was surprised when you said that the proof of theorem 2 is basically the same as that of theorem 1. Is that literally true? Because if alpha is close to 1/2, I think you have this A+ and A-, which look very different, and they appear like nearest in neighbors and so on. So you have to treat the mixture of A+ and A-, isn't it true? So then I didn't think it's close to, it's similar as the case where you only had this A star.
Well, I cannot give a technical explanation, but of course it's not exactly the same. So you have to take the old proof. You have to take 2 indices instead of 1 index, and then you have to insert judiciously factors of alpha and 1 minus alpha in various terms. But the reason why it's almost exactly the same is that there is no interference between A+ and A-. They don't talk to each other. So B talks to both of them. And you want to reduce B. So you know, when B talks to A+, you have to do something. When B talks to A-, you have to do something. But that's exactly the same thing that we were doing in the other proof. So alpha equals 1/2 is not a problematic point for the RG. So the problematic points are alpha equals 1 and alpha equals 0. Because near these points, it makes kind of no sense to separate, you know, when we write A in this form, you know, it makes sense only if alpha is not too close to 0, 1. Because if alpha is, say, close to 1, then, okay, this term is very small, and it makes kind of no sense to insist that the correction has to be separated into A- plus B. So here something changes. So in fact, this new RG map that we construct in theorem 2, it doesn't work near alpha equal 1 and near alpha equal 0. So you have to run the RG map until you enter these regions, and then you switch to the other RG map from theorem 1. And this is because somewhere in our theorem 2, in the RG map, the factors of 1 over alpha and 1 over 1 minus alpha appear. So those factors are the problematic ones.
Okay, yeah, thank you.
Yeah, I was curious about the role of dimensionality. I mean, would this work in 3 dimensions, or all your pictures are in 2 dimensions? And also, of course, the result is going to be completely different in 1 dimension. So maybe you could comment on that.
I have no doubt that this will work in 3 dimensions, but we haven't worked this out. And I think it would be interesting to check indeed that this works. There could be some interesting details. For example, this theory of disentangling, it could require some new tricks in 3 dimensions compared to 2 dimensions, because disentanglers find a particular effect. And until I check this in detail, I don't know how that effect will manifest itself in 3D and what exactly one should do to kill it. But I'm sure some other trick will work. It's going to be an easy trick, but I'm just not sure if it's going to be exactly the same trick. You also asked about 1D. Well, 1D RG is very easy for lattice models. It's just a transfer matrix. So yeah, if you wish transfer matrix in 1D, you can view it as a form of Tensor RG. So yes, it works, but it doesn't need disentanglers. So it's much easier.
Yes. Okay. Yeah. Thank you.
So
Well,
I have
if
a
you look
question.
at the-
Oh, sorry.
Excuse me.
Yeah. Who is that?
This is Tom Spencer.
Oh,
I
hi.
was just
Sorry.
gonna
Yeah.
wonder about if you have a magnetic field in 2 dimensions, then of course you should flow to the high temperature fixed point, for any strength of the field. And is that something you can see with these kinds of techniques, or do you need something better?
Yeah, it's true that in my exposition here, I said small magnetic field here.
But you also
I
have,
can,
yeah.
Yeah, but I agree with what you're saying. It should be, it should flow for any magnetic field, but I can't answer at the top of my head if it follows from the theorems that you prove or it requires some extra work. Maybe Tom can say something.
I'm not sure I understand the question. Arbitrary magnetic field just corresponds to alpha ranging from 0 to 1.
No, what Tom is asking is, suppose that I'm at high temperatures. His question is about theorem 1.
So for any temperature, right? I mean, you put a magnetic field in, you're going to decay. You're going to flow to the high temperature fixed point somehow. Everything's going to decay exponentially.
I don't know.
Well, how?
I mean, that's of course
no, Tom,
theorem,
I understand your question. Of course, so your question is about kind of topology of. Let me find some empty page so that I can draw a picture. So what we discussed with Tom is what happens. Here there was a kind of a diagram, and we would flow to the neighborhood of this point and to the neighborhood of this point, or here at high temperature we would flow to the neighborhood of this point. But it seems to me what you are saying is that in fact, from the point of view of a phase, here and here, there's no phase transition between these two things. So there's kind of a whole region here.
Exactly, yeah.
Which corresponds to a disordered physics.
Which should be in the same universality class as the high temperature, right? I mean, you expect it to be. Maybe there's something I'm missing here, but.
Yeah, it should be in the same class, but I'm just not sure if that region is covered by our theorems. Yeah, I cannot answer, sorry, but it's a natural question. It's just somehow it didn't occur to me to think about this before, but I'll think about this and I'll email you.
Okay. Thanks very much for a very interesting talk.
There is a question on the chat. So maybe let me read it. Or rather a comment.
Yeah, I can see
yeah,
the question.
Can you see it? Yeah.
Yeah.
Yeah, I should probably read it for people. Yeah. I think the fact that we have A+ and A- is because of the Z2 nature of Ising model. I wonder if, for example, we have an n-fold clock model, can we still approach the low T fixed point through the same way? It seems not very straightforward to me.
It's absolutely straightforward. As I said, the proof of theorem 2 was just made by making one index, two indices. So now you have to have three indices. The proof is exactly the same. So theorem 2 is going to generalize to n states and to n coexistent states. When you study the properties of the free energy and the properties of magnetization, you will have to work a little bit harder than what we did with Tom, because, well, because the topology change, there's more complicated topology. Simply, you have here we just had a single line which was surface which was separating the two phases. With more phases, you will have more complicated lines. So, but I'm sure that this can be done. Yeah.
Did you cover the case where you have some symmetry breaking terms so that your pictures showed that it wasn't necessarily exactly mu equals 0, the transition, it might have been slightly off because of some extra terms. Is that the case?
Yeah. Well, I was drawing this picture. Like this. Yeah. What John, I think, is referring to is that I was drawing this coexistence line, coexistence surface, the stable manifold, kind of not exactly at alpha equal 1/2. Well, it's because this theorem that we proved, it applies for any B, which doesn't necessarily preserve Z2 flip symmetry. But if the B preserves the Z2 flip symmetry, then of course alpha critical of such a B has to be equal to 1/2.
Okay, good. Thank you.
Yeah, another question. So you didn't talk about the details of the disentangler, but is it something you can easily find, or is there any? What kind of? Are there many disentanglers, and some do well and some do bad, or something like that? Or sorry. The question.
Well, I can give you some very simple. Yeah, I'll just give a very simple example. So you take this tensor x. So I said, okay, x, y, something like that, and you look at its components. And for example, one interesting component could be is if all these indices are 0, but these indices on the right side are non-zero. That's kind of a component that typically you have to find. Mm-hmm. And then you choose. What you now have to do is that you choose here a rotation. You have to choose a new basis in the space of two indices. Basically, a rotation which eliminates these components. So in the new basis, this component is not going. In the new basis, this component is 0. So the disentangling then is just a rotation. You have a vector and then you rotate it along the 0 direction, because you want your tensor to have big 0 components and all the other components have to be small. So
okay, so in that case, it's kind of automatic to find disentangler.
It's kind of automatic to find a disentangler, but it is a little bit more tricky. Once you rotated this component away, you still have to decompose your tensor as the product of two tensors,
Oh,
x
yes.
prime times y prime.
Oh.
So you have to make sure that that is also possible. And so this, you have to work a little bit to ensure that this is possible.
Is it something guaranteed, or is it something you don't know if it works until?
It's not guaranteed. No, it's not guaranteed. So in finite dimensional context, of course it is, but here it's not. So basically, so our disentangler R is chosen as an exponential of some simpler map. You know, let me call it rho. And if this map rho by itself is a contraction of two tensors, then it's guaranteed that you will be able to decompose as x prime. After applying the disentangler, you will be able to decompose it as x prime with y prime. So in fact, that's, and we in fact always do it like this. So our rho is always the contraction of two tensors, rho up and rho down. But that's a pretty technical point. So.
Okay, yeah, thank you very much.
Any more questions?
Yeah, I have one other question. Do you foresee this working when you have continuous symmetry in the low temperature phase as well? Of course, you've got to go to higher dimensions, but
so I think that this tensor network representation of lattice models, it could be useful. It could be extremely useful for any lattice models. It could be useful for gauge theories. It could be useful for ON models. It could be useful even for Gaussian fixed points.
Mm-hmm.
You know, because if you think about this, you know, we know that the Gaussian fixed point neighborhood is, yeah. So we know how to do RG near the Gaussian fixed points. But it's still pretty technical because people who do this RG near the Gaussian fixed points, they have to be very creative about inventing all sorts of fancy norms, and then it lives in some space of polymers and whatnot to control irrelevant directions. At the end of the day, it gets pretty sophisticated for a non-expert. So here, everything is controlled by Hilbert-Schmidt norm. So I think, you know, it is very worthwhile to think what this language could give for other models, either to simplify known results or maybe to prove new results.
Jan, you had a question?
Yeah, you mentioned that if the bond, the indices of the bond are numbered by natural numbers, then after this renormalization group, they are labeled by the product of two natural numbers. So, and then you want to order this. So is it relevant how you order, or it's, I mean, you can order in many ways, and it seems kind of arbitrary.
Yeah, there is a lot of arbitrariness at this step. So, of course, if you pick a completely random order, you won't find a fixed point. So you have to order in such a way that that 0, 0 component is mapped back to 0.
Yep.
But apart from that, everything else in our work, everything else was completely arbitrary. It doesn't affect the norm of the norm goes to 0 and that's it. Now, when we do the critical fixed point, it's no longer going to be the case. There, this issue is going to be more important.
Thank you.
Okay.
Okay, anyone else? Okay, maybe that's the time to finish at least the official discussion. So thank you, Slava, again for this very nice talk.